In the name of IEEE Boston, I would like to thank everyone for being here today. And to start, I would like to talk to you a little bit about IEEE Boston section. Boston section is celebrating 101 years this month. And as one of the oldest sections, we are a very robust group of almost 7,000 members. And in total, 42 groups between technical societies and affinity groups, with more than half of our members actively participating in one or more of these groups. COVID interrupted a lot of the volunteer community across the world, and we were not the exception. We are currently working to pick up and increase the previous pace and size of our community. In the last couple of months, 700 new people just started volunteering at some of our IEEE groups around Boston. Boston is a city of colleges, and our section have members from 20 different academic institutions, almost 500 graduate students, and around 300 undergraduate students. And MIT is the most representative one, with 271 students being member. Boston is also one of the best places to develop research and technology. At any given week, you can find at least 2 different events happening around the city. Because of this bursting, vivid environment, we can have the privilege of celebrating 3 milestones here today at the same time. There is a huge history of partnership between MIT Lincoln Labs and IEEE Boston. We currently have at least 107 workers from the Lincoln Labs that are members involved with IEEE. As part of this huge partnership, which bursts innovations, we are here today to celebrate the unveiling of these 3 milestones. The IEEE Milestones Program honors significant technical achievements in all areas associated with IEEE. Milestones recognize the technological innovation and excellence for the benefit of humanity, found in unique products, services, seminal papers, and patents. I would like to thank everyone that helped to make this celebration happen, especially Gilmore Cook, Bob Alonji, and Joseph Campbell, who helped a lot. Okay, and make this happen today. Now, I would like to introduce to you Karen Panetta, that will be our Milestones Master of Ceremony.
Thank you, everyone. And thank you so much to MIT Lincoln Labs and Director Evans for having us here today. It's always a pleasure to come back. And in case you don't know, MIT Lincoln Labs has hosted many milestones here. So we're very proud of it. And we're also very proud of all those IEEE fellows that you've got listed out there. So you lead industry here in Massachusetts for your involvement and engagement with IEEE. So thank you so much for that. I also want to thank all of our Boston section members who have helped us put this together. And for those of you that have worked tirelessly to make this event come off today, as it will be such an exciting one for all of us. And I want to welcome so many of our milestone family members and our inventors that have made these innovations possible. And we really celebrate you today as well. So with that, I would like to introduce our IEEE Region 1 Director. And for those of you that don't know what Region 1 is, that is the Northeast of all IEEE. So I'm going to introduce Bala Prasanna. Bala is the professional career of 35 years who's been working at institutions like SUNY State, University of New York, AT&T, and IBM in various roles in senior and technical management positions. He volunteers his time as a board member of IEEE USA, and he's a very proud member of the IEEE Eta Kappa Nu HKN Honor Society. And since you have so many IEEE members here that are doing such wonderful scholarly work and contributions, please do nominate them for membership in IEEE HKN. It's a wonderful designation to recognize all of your wonderful contributions. Bala also cherishes his time with students and has been a speaker at various US and international universities on career management skills to survive and thrive in today's workplace. His passions are photography, reading biographies, and meeting people of accomplishment. He is so accomplished and he connects us to people all around the world. And we're very proud to have him as our Region 1 Director. So please welcome Bala.
Hi, good afternoon. Good afternoon, Director Eric Evans, Dr. Joe Campbell, I think I saw him somewhere right there. IEEE President-elect Dr. Kathleen Kramer, Boston Section Chair Myra, Dr. Karen Panetta, Robert Colburn from IEEE History Center, and Richard Rediker, Susan Ziegler, Robert Lax, and all distinguished members in the audience. Good afternoon. It is an honor and privilege to be speaking before you as IEEE Region Director at this IEEE milestone dedication event at the esteemed MIT Lincoln Labs. Significant discoveries and inventions from older times have left an indelible mark on society, shaping human civilization in profound ways. From the invention of the wheel, which revolutionized transportation and trade networks, to the discovery of agriculture, fundamentally altering human settlement patterns and food production, and from the invention of the printing press, democratizing access to information and knowledge, to the harnessing of steam power during the Industrial Revolution, catalyzing mass production and urbanization. These milestones have shaped the fabric of our existence, influenced how we work, how we live, and how we interact with the world around us. In recent years, we have been witness to remarkable innovations, and their impact on society have been just as profound. From the semiconductor age, revolutionizing the electronics industry, to the ARPANET internet age, connecting computers globally, wireless communication enabling seamless connectivity, advances in renewable energy, artificial intelligence. These developments in recent days have transformed the way we live, communicate, and interact with technology. IEEE milestones are significant technical achievements recognized by IEEE for their importance and their positive impact on humanity. They symbolize technological excellence and serve as a source of inspiration for future generations of engineers and scientists. As of December 2023, IEEE had 243 milestone dedications, with Region 1, Northeastern region, contributing about 46. That's a little around 25%. And particularly the Boston section contributing 11 milestone dedications. That's still a very high percentage. Congratulations. That excluding today's milestones. So you're already ahead of the game. Dr. Campbell's question about how Region 1 plans to lead in this area is pivotal. We aim to cultivate relationships across various stakeholders, including milestone proposers, advocates, local government, companies, civic groups. Collaboration is the key. Two examples in recent days to cite are Project ECHO, where we have industry, local government, civic groups, educational institutions are engaged and involved. And the other example is French transatlantic telegraph cable of 1898, but the milestone dedication happened in 2018. This had the support of local businesses and it attracted large crowd. Our dedicated milestone history coordinators, Dr. Ram Darjati and Dr. Ron Brown, are spearheading efforts to identify and support new milestone candidates across our 22 sections. Boston included. With the support of Director Mike Gizilowitz and Robert Colburn, we have a pool of approximately 50 potential milestones for consideration. This lays a solid foundation for us in Region 1 for future initiatives. I am also pleased to inform you that Region 1 helps the section with $250 per milestone when the dedication event is announced. $750 in the bag for you. So you probably heard of our honor society, Ada Kappa Nu. We aim to confer eminent honorary memberships to deserving inventors. For instance, Dr. Robert Wilson of Big Bang Theory fame, he's in our neighborhood in Homedale, a Nobel laureate. His nomination as an eminent member is underway. So I think your help is also needed, Karen. With potential recognition at the Project Echo milestone dedication event that's likely to happen sometime in spring or summer of this year. The merger of Region 1 with Mid-Atlantic Region 2, Dr. Drew Lowry is here, Region 2 Director. This merger presents exciting opportunities for collaboration, particularly in milestone initiatives. With Region 2 recently approving a milestone, which we did back in January, just a few weeks back. And there are 22 potential candidates. The joint effort could yield a substantial number of milestones. Joe, that's the answer to your question. So we have about 72. Furthering our commitment to advancing technology for humanity. In closing, milestone dedications serve as public affirmations of our dedication to technological progress. We embrace this responsibility with humility and dedication, recognizing its significance in shaping our collective future. Thank you all.
The history of MIT Lincoln Labs is, very rich, and there's no one better to tell it than its director, Dr. Eric Evans. Eric Evans was appointed as director of MIT Lincoln Laboratory in July of 2006. As director, he was responsible for the laboratory's strategic direction, overall technical and administrative operations. Dr. Evans joined Lincoln Laboratory in 1988 and held positions in increasing responsibility in air and missile defense technologies. Dr. Evans is currently the chair of the Defense Science Board, of which he has been a member since 2009. He is also an IEEE Fellow, AIAA Fellow, and a member of the National Academy of Engineering. He holds the BS, MS, and PhD degrees in electrical engineering from Ohio State University. So he will be speaking for us, but I also want to thank you for your service for our National Science Defense Board. Thank you so much for all your service to helping keep us all safe. So with that, please welcome Dr. Eric Evans.
Karen, thank you, and good afternoon. It is a privilege to have you all here. For everybody from the outside, welcome to Lincoln Laboratory. And we really appreciate the IEEE President-elect Kathleen Kramer for being here today. And it's just wonderful to have so many IEEE people from the Boston section here as well. Thank you for joining us and helping us to recognize the great talent that has contributed to these milestones over their many years of work. I'll be giving a very brief overview of Lincoln Laboratory, so I could give an hour-long briefing, but don't worry, we're just gonna go for a few minutes. And I wanted just to cover some of the background from the beginning because it drives what comes later on. And if I could have the next chart, please. So Lincoln Laboratory was set up in 1951 to develop a system to defend the US against the Soviet bomber threat. We were very worried at the time about Soviet bombers with nuclear weapons, possibly flying over the North Pole in a surprise attack. And the US needed to have a better air defense capability to defend against that. And we had significant staff that came over from the MIT Radiation Laboratory to start Lincoln Laboratory. I think some of you know the background there. The MIT Rad Lab created half of all the radars used in World War II, and did a lot of work to advance the state of the art. Many of those people and many of those ideas came to Lincoln Laboratory in 1951 when it was started up for the air defense system development. And what we put together, working with many across the community at the time, was a new system that had radars on the ground, at sea, and in the air that could be connected to interceptor fighters and guided missiles through the first implementation of a real-time computer for a defense system. So major, major step in processing. And that was based on the Whirlwind computer, which was recognized by an IEEE Milestone Award years ago. And this whole system has been recognized with an IEEE Milestone Award here. And there are some major technologies that came through this. Very interesting. The first real-time computer I mentioned for a weapons system. Digital communication techniques, special codes were developed to transmit data across telephone lines. We advanced magnetic core memory technology, and this was the first time there was a good human-machine interface with LightPen CRT interactive approaches to work with the data and figure out what was happening out there. And so Lincoln developed the prototype for this over about 7 years. And then in 1958, it was ready to acquire it. And the MITRE Corporation was spun off from Lincoln Laboratory to get it out there. And this helped to defend the US for many, many years. And so this is a part of our roots, and our mission number has gone up since then. We've gone from air defense to a whole range of mission areas. I'll mention that briefly in a minute. But I wanted to say a little bit more about some history that is embedded within the MIT Rad Lab and Lincoln. So just outside the auditorium, over here, you'll see a radar system that's called the SCR 584. So this was a fire control radar system built by the MIT Rad Lab back in World War II to defend against airborne targets. It could direct fire, and it was a major system for the defense against the V-1 cruise missile. And this is the radar system that resulted in about 1,700 systems being developed by contractors and deployed mainly over in Europe. And it was a major factor in the success in winning the European aspect of World War II. So this was the system that after the Rad Lab was closed down on campus at MIT, was then moved to Lincoln Laboratory. And it jump-started all the radar work at Lincoln for air defense, and really drove some of the early work in the early mid-50s for the prototyping work we were doing for SAGE. So many years ago, we thought, you know, this is such a historical system. We, Lincoln Laboratory, ought to at least have an antenna dish or something here that we can point to, you know, as a part of our heritage. So we looked for years. We had people you know, calling various bases around the US. We had people looking around Europe, and we couldn't find anything. We were worried that the last one had been just destroyed and gone or something. But we did find something eventually. So one night we were searching on eBay, and there was a system up in a farmer's barn in Maine. So we immediately sent people up to take a look at it. We bought it at a low price. Brought it down. It had the full trailer, the antenna, of course, and all the electronics, all the receiving systems, the processing system, everything. One of the real treats in this is over here. If you get a chance to take a look, we have one of the original cavity magnetrons that was embedded in the system. And this was a design that came over to the US from the UK to help jumpstart the radar effort within the radiation laboratory. So this is a very historical piece of technology, and we're just so pleased to have it here today. And I just wanted to mention that because you'll see it out there, and this was a major driver for the success of Lincoln Laboratory early in the 50s and mid-50s. So this is how we look now. We are what's called a federally funded research and development center, FFRDC. We're run by MIT. All of us who work here are MIT employees. Our mission is technology in support of national security. And we have many key roles, but the three big ones are what we call system architecture engineering. So we look at how big systems come together, what sensors and networks, and in some cases weapons around new problems. We do long-term technology development. So we might look out 10 to 15 years in a technology area to get it ready to be integrated into systems later on. And then we do system prototyping and demonstration on a grand scale. At any given time, we have about 25 or so very large prototypes underway at the scale of $20 to $350 million over a few years. So our role is to take on projects which are high risk and high payoff, and to create the existence proof for the first copy of something that might be dramatically new. And then when we're done, we transition everything out of Lincoln and we move on to the next problem. And that pretty much spans all the mission areas that we have here now. We're doing a lot of air defense work still, missile defense, lots of homeland protection work, communication system work, a lot of cybersecurity work that spans almost everything that we do here. We're doing a lot of work with the Space Force to help to protect our satellite systems. And we do a lot of work in ground surveillance to help protect operational forces in harm's way. And recently, we created a new biotechnology and human systems division, partly driven by the needs for the pandemic. And that's been growing very rapidly here. Some call that the new nanotechnology for the laboratory. Last year, our funding was about $1.4 billion. We have about 700 programs. We're about 4,500 employees here. And that's about 70% technical. So a lot of very good people here. Many of us say the best part of working at Lincoln is the amazing talent we have here, and many are in this room here. So that's what we do in one chart. This is the model for how we like to develop technology. We try to get the input from the people who actually use the systems out there. And then we analyze what's going on. We take technology inside the laboratory or outside, and we bring it together around new ideas we might have. When an idea is ready, we might prototype something, sometimes rapidly if we can, at the scale I mentioned. And then we transition in two ways. One way is directly across to operational forces. We had a fair amount go directly from Lincoln over to Iraq and Afghanistan as needed. And then the balance goes into the industrial base to be produced at the scale needed for the DoD and others. And what we're doing more and more now is transitioning technology to commercial companies, sometimes startup companies. And we're trying to encourage more and more of that type of tech transfer out of the laboratory. In any given year, we might have between 25 and 50 technologies shift out of Lincoln in some form. And these could be robots to find improvised explosive devices, new comm terminals, cybersecurity software, new subcomponents for sensing in infrared or optical bands, new radars, or new biological agents and identification systems. And they go out and get produced at a significant level in many cases, and they're out there being used right now. So our product is really getting technology out of here, and that's what we're striving to do every year. So just to look more broadly at the technologies that have gotten out of Lincoln over the past 70 plus years, if you go back in the 50s and 60s, I talked about some of this already, but many digital coding techniques came out. The Reed-Solomon codes came out of Lincoln. The first television picture transmission by a satellite was driven by a Lincoln program. In the center here, we were the developers of the first packetized speech approaches, and this technology was recognized with an IEEE Milestone Award. We do a lot of FAA work, some of that for traffic collision avoidance, but also the Mode S system is grown up within that program to be recognized today. We do a lot of 3D laser imaging work, some of it for the DoD, some of it for many other sponsors, and a lot of that technology was driven by the solid state laser development. It was developed early in the 60s to be recognized today. And then so much of the work at Lincoln is driven by our microelectronics work. And this 193 nanometer optical lithography work to be recognized today has been a major driver for new technology inside and of course outside of the laboratory. And we're very proud of the contributions for the team in that area for so many years. So there are a wide range of areas that we're involved in. And just to step back a little bit and think about what's next for us. These are the areas I mentioned before on the first overview chart of Lincoln. Some of them are new. We've been going through what we call a mission shift here over a few years to align to the most significant national security challenges. This is a very, I'd say, difficult time for how fast the technology is creating new threats that we have to worry about. So we've evolved. I mentioned cybersecurity. We're doing a lot more with ground surveillance, and I mentioned biotechnology and human systems. As we look ahead, what we see is a whole body of new work in cyber and electronic warfare. Those areas are merging in a sense, and we're helping to lead the way for some of that, working with others across the community. We're doing much more work in national security space to help to protect the US assets. And we expect to do more work with NASA over the years. There's overlap with work that we're doing in the national security world. And we're even getting involved in climate change technology development work. So some view, and we view, that climate change is one of the biggest global security problems now, that we should be developing new technology to help. And then embedded in all this is new technology work in artificial intelligence and autonomy, quantum information science, very interesting area, and counter-influence operations. Some call that gray zone warfare. There's a lot of psychology, sociology, and data integration work as a part of that we're exploring. So much work on the horizon. And as we're moving into these areas, what we're striving for, what we hope for, is that we do work that someday, decades from now, will be recognized with IEEE milestone awards. So if you're interested in more of the background, we have this document we put out for our 70th anniversary a couple of years ago, 70 innovations over 70 years. It covers some of the areas I covered, but many others. If you'd like a copy, just let us know. We'll send it to you. But I find it to be a very interesting document, and some of it's hardware, some of it's software, but you can see how it all fits together with the overall evolution of the laboratory. So we are just so pleased to be recognized with 3 more IEEE milestone awards. These are the 3 that we've been connected to so far. We'll be receiving these today, of course. And I was talking with some of you. We plan to put these on a large area, a large board, right at the front door of the laboratory, so all can see. And we will be very pleased to get that up as soon as we can. And we're just so proud of these, and we want everyone who comes in to see them. So with that, I'll stop, and I'll look forward to talking with many of you more. If you have any questions at the reception. And again, thank you for joining us, and congratulations to everybody involved in these milestone recognitions. So thank you.
So IEEE milestones don't just recognize the technical accomplishments. They have another goal, and that is to promote the technology to the general public. So while we have milestones here, they're everywhere in Boston. So for those of you that go to Park Street Station, there's one outside there for the first electrified subway. And there's another one in Jamaica Plain near the zoo, the Franklin Park Zoo, for the first electrified fire alarm system. So those are fun trivia for you to use with your grandchildren, children, and students, just so if you're doing treasure hunts. But they're everywhere, and it really is communicating the impact of technology, not just for history purposes, but to also stimulate the next generation of innovators and technologists and engineers. So our next speaker is going to clarify for all of us how important in the impact of the Mode S air traffic control radar beacon system. And to do that, we're going to call upon James Flavin, who is a principal staff in the Homeland Protection and Air Traffic Control Division at MIT Lincoln Laboratory. And prior to this role, James served as the division head, where he was responsible for research, development, evaluation, and technology transfer for surveillance technology and decision support architectures spanning air traffic control, efficiency, airport surface safety, air traffic, collision avoidance, and border surveillance and homeland air defense. He joined Lincoln Laboratory in 1986, and he holds a Bachelor of Science degree in Electrical Engineering from Northeastern, my alma mater, good work, James, and a MS in Electrical Engineering from the University of Michigan at Ann Arbor. So let's welcome James.
So thank you. So it's truly an honor to have the opportunity to provide this brief history of the Mode S air traffic control radar beacon system. What I thought I would do is just start off by talking about the emergence of beacon radars for air traffic control, and what some of the problems were that existed at the time the decision was made to develop Mode-S. And then I'll talk about the Mode-S development and its impacts. So the use of radar for air traffic control goes back to 1947, leveraging a lot of the radar technology developed for World War II. And at that time, well into the mid-1960s, there was letters I was going to show from President Kennedy and such, but the belief was that air traffic control, that function could be served by the semi-automatic ground environment that Eric mentioned in the second slide of his talk. However, by the mid-1960s, they saw the situation very differently. And so this is a well worn out cover. It's the best shaped cover of a report I could find of the Air Traffic Control Advisory Committee report written in 1969. And many distinguished leaders from the private sector, as well as Jack Rowena from MIT campus, were on this committee. And what they described was the air traffic control system as being in crisis, that there had been unforeseen growth through the 50s and 60s, and it was seen as really having limited capacity for additional growth. And of course, delays arising at airports, there were safety concerns. So this was a highly technical 2-volume report that made a number of recommendations, which included improving the existing radar beacon tracking system and actually adding a data link to reduce the amount of workload for voice traffic that was taking place between pilots and controllers. And also to develop an automated collision avoidance system and then fully automate the air traffic control system. And as you'll see is these two were done and we're still working on this one. And however, one of the constraints placed on by the report was that this transition needed to be backward compatible with existing systems. They wanted to improve the system, but not slow things down or make things less safe during the transition. So, so what is an air traffic control radar beacon system? If you go to any airport of significant size throughout the United States or really throughout the world, you'll see an antenna configuration that looks like this. I can't unsee these when I go to an airport. So it's actually two radar systems that are pretty well integrated together. The bottom one here is the dish for a traditional radar. It transmits a pulse of electromagnetic energy, reflects off the object of interest, gets processed and displayed to an operator. The family of radars that Mode-S belongs to is called secondary or beacon radar. And what you really have here is an array of dipoles. And the way that worked really prior to the development of Mode-S, the technology that was widespread use was called ATCRABS, Air Traffic Control Radar Beacon System. And its origins derived out of the identification friend-to-foe system developed for World War II. And its major elements were a ground radar. There's a cartoon of the radar I just showed you in a moment. And it basically sends up very simple interrogations, 3 pulses, P1, P2, P3. The P1 and P3 go out of the main beam of the radar, and depending upon how far separated they are in time, the aircraft transponder, they haven't talked about, receives those and responds either with the identity of the aircraft or its altitude. And then there's this squirrely little P2 that's transmitted omnidirectionally, and that's for something called interrogator side lobe suppression. But that basically tells the transponder that it's not responding to a side lobe. So it's a very simple system, works great. The position report is really, there's a lot of interrogations and replies as the antenna spins around, and it picks the center, and that's the bearing. And then depending upon the time it takes for the reply to come back, that's the range. So it's a very simple system. Of course, the challenge is there's a lot of interrogations as the system grows and lots of planes giving very similar replies, and those replies interfere with each other. And 2 significant shortcomings. One is something called synchronous garbling. In situations where you have aircraft close is when you want the radar to work, but that isn't the case, because if they're similar in range, the replies overlap and it becomes very difficult to decode them. And then if replies are missing, since the bearing is determined by picking the center of a sort of a machine gun of interrogations and replies, if one's missing, it gets the bearing wrong. And then if there's enough replies remaining, it actually creates a ghost aircraft. So that brings us to Mode-S. So remember the P1, P2, P3 pulse. Mode-S, basically, the basic idea is you have a more complex interrogation, right? So there's the P1 and P2 transmitted co-amplitude to keep the ATCRABS transponders from responding to a data field. You can send data now from the radar up to the aircraft. And then within that data field is an address. So every aircraft in the world would have its own unique address. It's actually hardwired into the back of a Mode S transponder. And when that Mode S transponder sees its address, it replies with data, more information about the aircraft state, plus that address to tell the ground radar, I got your interrogation, here's your reply. Of course, the actual implementation of Mode S is quite a bit more complex. And all I can say is I don't have time to go through all of that complexity, but really in preparing for this talk, I went through really hundreds of extremely well-written reports by people whose names and names beyond that I'll show you today. But there was exquisite work done developing the signal set. And this is just a couple of signals shown here. And without saying is these signal sets form the foundation for not only the Mode S radar, but significant systems beyond there, including collision avoidance systems and automatic dependent surveillance broadcast, parallel runway monitors, and also surface surveillance. And then on top of the signal set, so again, it achieved a 4 megabit per second uplink, a phenomenal speed for the 1970s, and 1 megabit per second downlink. There was significant trade-off analysis and algorithm work and advancement in other areas to make Mode S work. Most notably, an advanced planar array design, 340 or so elements, designed to be low cost. And to show how good this design was, it not only worked extremely well, but it's actually the antennas that were deployed that went into production in the early 1990s are still in the field, sitting in the elements and still working. The new planar array essentially supported a couple of beams coming out of the radar, essentially enabling a monopulse receiver to be hooked up to it. So instead of needing a whole bunch of interrogations and replies to determine the bearing, you can do it in one pulse. We typically do it in one interrogation. And then there was a range of other algorithms. And also most notably is that data link applications were developed in the early going to motivate aircraft and pilots to equip with Mode S transponders, specifically traffic information service that could tell a pilot when the aircraft approximate to its own, and also graphical weather service to tell a pilot if they were flying into hazardous weather. So lots of concepts, lots of analysis, lots of design reports. So it was necessary to bring it all together into a prototype. And the first prototype of Mode S was called the Transportable Measurement Facility, or TMF. And essentially it wasn't the whole Mode S radar. It essentially included the advanced interrogator, pulse quantizers, and receiver processing. And then really for its time, very exquisite data recording. And the TMF was taken all around the country and really deployed, co-located with the ACRABS radars that were having problems. Data was recorded and analysis was done on that data to compare performance and also validate the Mode S concepts, algorithms using real data. And based upon the success showing better track initiation, track integrity, elimination of interference, the decision was made in the early 1970s to have Texas Instruments build 3 engineering prototypes. And the Texas Instrument engineering prototype is shown here, and it's actually next to an Ares simulator. So there weren't a lot of Mode S transponders out there. So the laboratory built a simulator that could essentially load test the prototype with 400 aircraft. And so engineering prototypes were deployed here at Lincoln Laboratory. One was deployed at the FAA's Technical Center in Atlantic City, New Jersey. And here at Lincoln Laboratory, up on Katahdin Hill, just a couple of 100 yards away, was the first prototype of the planar array, the shoebox-shaped antenna shown here. And all of this really was brought together in an end-to-end system, including controller-like displays to allow the Mode S concept to be fully vetted. And by the 1990s, a decision had made to have Unisys, now Lockheed Martin, produce 135 redundant configuration radars for deployment to the major airports throughout the United States. And so we were finally able to get rid of our shoebox antenna and replace it with a nice production antenna. And then the prototype was replaced by this redundant configuration from Unisys. So there's an aircraft in here. And so significant work also took place in prototyping the avionics. There was the airborne measurement facility. There were a lot of rumors, sort of perceptions out there as to what the pulse environment was at a busy airport. because it's not just about the planes, it's about reflections and other interferers that may be there. So AMF was flown all over the country to understand pulse environments, drive design decisions. It would support from the Lincoln Laboratory Flight Facility and experimental aircraft from the FAA, various airborne antenna configurations and transponder designs were checked out. And by the early 1970s, the prototype MODES transponders were beginning to look very much like the type of transponder you would buy today. And shown here on the lower left is some of the initial leadership team, including Paul Drouillet and Herb Weiss from Lincoln Laboratory, and also Marty Przeski deserves mention. He was the associate administrator for FAA. He's the one that really led a lot of this technical effort out of the government side. So by the late 1970s, there was a desire of this leadership team to really expand the use of MODES beyond the United States, to really make it an international standard. And by the 1980s, standards committees were forming. Here's a picture of a tripartite committee that of all things involves the Brezhnev era Soviet Union, the United States and the UK. And by the mid-1990s, standards work was taking place in Asia. And of course, there are many people involved and you might recognize some of those faces. I know I do, but there's one face that sort of remains in common, both through publications and in the photos, and that is of Vince Orlando, who will come up with Eric during the dedication portion of this and receive the plaque for MODES. And so what's the overall impact? So today, if you're on an aircraft flying anywhere in the world, your aircraft will be safe and it'll be under the surveillance of a MODES radar. Just showing the radars in the United States, 387 radars, both in airport and en route configurations, a blanket the country. In Eurocontrol, there's nearly 650 radars, and I'm also not showing an additional 130 radars that are in their Middle Eastern section. And of course, I don't have access to the data in China and other parts of the world, but they have MODES radars as well. And then safety, right? So take it back to 1969, was a little bit to the left of this, the air traffic control system in crisis, no capability for future growth. As you can see, exponential growth has continued, yet the probability of a mid-air collision has gone down dramatically. It's not just MODES, but it's MODES, the systems it enables, and other improvements have contributed to this incredible safe means of transportation. So just some acknowledgements. First, to the FAA for their longstanding sponsorship, leadership, and technical contributions in the development of MODES. The Department of Defense for their early pioneering work in the development of radars, and they were a strong sponsor and supporter of the developing of these international standards. Industry, so many companies have come and gone, but they were key in developing the early prototypes and bringing the system to production. And then of course, the organizations involved in developing international standards. And so finally, just some names. So as I went through and preparing for this, seeing all the reports, many names I've recognized and many people I know. And then there are people I'm sure that I've left off. But congratulations to you all and thank you for your contribution to the development of MODES.
Well, I wish I had seen that before I got on that flight from LA last night back that had hit massive turbulence. But thank you for that. Our next presentation is on the 193 nanometer projection photolithography, and that's going to be by Craig Keats. Craig is the associate head of the Advanced Technology Division and director of operations for the Microelectronics Laboratory at MIT Lincoln Labs. The Advanced Technology Division performs research in high-performance imaging sensors, deeply scaled silicon microelectronics, solid-state lasers, optoelectronics, superconductive devices, and biological sensors. Mr. Keats, or Dr. Keats, began his career at MIT Lincoln Laboratory in 1981 as a semiconductor process technician before holding positions of increasing responsibility in the advanced electronics areas. Dr. Keats holds a BA from Hamilton College and the SM and EE and PhD degrees from electrical engineering and computer science from MIT. So let's welcome Dr. Keats.
I too am honored to be here to tell you a little bit more about the development of 193 nanometer projection lithography here at Lincoln Laboratory, which happened from the mid-1980s to the mid-1990s in collaboration with a number of industry partners. So I'm going to start off with describing what projection photolithography is, because some of you may not know what that is, but any of you that have used an electronic device since the 1980s have benefited from projection photolithography. This is the technique that's been used to make every modern integrated circuit since then. And it's basically an optical scheme where here you have, an illuminator, some illumination optics. It goes through a condenser lens, through a photomask, which actually contains the information that you ultimately are going to print on a wafer. It goes through this projection lens that does a photo reduction process, and it prints it onto a sensitive layer that's actually on a wafer itself. So I'm going to show you some of it. This is a photomask. It's actually came out of our 193 nanometer lithography system here at Lincoln Laboratory. It is a 1/4 inch piece of quartz glass that has anywhere, depending on the complexity of the circuit, from 1 million to 1 billion fine quartz chrome features that are patterned on this substrate. This ultimately gets projected through the lens onto a silicon wafer, which I'm showing there. And you'll notice it's a photo reduction process. So the mask master is larger than what you actually print on the wafer. Here I have an example of a 300 millimeter silicon wafer. And this has about 80 copies of that photomask printed down onto this substrate. Now, typically, these projection photolithography systems are referred to as steppers, wafer steppers, or steppers for short, because you're stepping this pattern across the wafer. And where that photomask is built in an E-beam lithography system, and it can take anywhere from hours to days to literally write all those features, you can print one of these wafers on a modern tool in 12 seconds. So it's a way to get much rapid patterning a lot faster. So the resolution of one of these systems, and this is the only equation I'm going to use today, but it's a very, very simple equation, all right? It depends on two things: the wavelength of the light that you use to do the illumination and the numerical aperture of that final projection lens. So if you want to make smaller features, you've got two knobs to turn. One is the wavelength. You go to shorter wavelengths for the light bulb that you're using to do the exposure, or you increase the numerical aperture of the lens. So, and we refer to that as the critical dimension, the CD, the minimum feature size that you can pattern in one of these systems. So what I'm showing here is a plot of the actual minimum feature size that's been used to make integrated circuits from the 1980s to the present day. And this is a semi-log plot, right? So that's an exponential scale on the left side. And then the year at which it was introduced on the right. And what I have here for a frame of reference is a human hair. For those of you who may not be, calibrated on what a micron is. And even in the 1980s, the minimum feature size used in an integrated circuit was anywhere from 2 to 5 microns. So we were already printing features that were 10 times smaller than the diameter of a human hair. So what I'm going to do now is start to fold in the lithography wavelength that was used to pattern those features as you're going along. So it started with what was called a G-line stepper. It used a 436 nanometer wavelength of light to do the exposure. Around the 1986-87 timeframe, we transferred to the I-line stepper that used a different wavelength at 365 nanometers. And at this time, people were beginning to get concerned that optical lithography was coming to its limits. And this is actually testimony made by Sonny Maynard, who was the director for computer and electronics technology at OSD, to the testimony to Congress, the House Armed Services Committee, and basically saying that optical lithography was coming to an end. X-ray is the future. And that actually led to DARPA, then called ARPA, starting a $1 billion advanced lithography program. And what they were really targeting there was development of X-ray lithography, because everybody thought optical was done. But there were some folks that thought there was still some life in optical, and some of these folks even from industry. And so what I'm showing there is a spectrum of a mercury vapor arc lamp. That was the illumination source that was being used in these lithography tools. And you'll see the G-line stepper there at 436 nanometers, the I-line stepper at 365. Industry felt that they could squeeze one more wavelength out of this light bulb at 254. But you'll notice that the intensity of that was quite low. There's actually researchers from IBM who realized that there was this new class of excimer lasers that was developed in sort of the mid-1970s, and that you might be able to use one of those excimer lasers, the krypton fluoride laser, which has an exposure wavelength, has a wavelength of 248 nanometers. It was close enough to that sort of 254 that they could use that wavelength and still use the same fused silica quartz material to make the lenses. Because one of the concerns was, as you were going to these shorter and shorter wavelengths, was whether or not the optical materials would be transparent enough to allow you to do that projection. So industry went ahead and built the first krypton fluoride 248 nanometer lasers. They again continued the scaling to smaller and smaller feature sizes for a number of years. And at the same time that this announcement came out and the government was making these huge investments in X-ray lithography, Lincoln Laboratory, sort of as a rogue, went and said, hey, how about we try that 193 nanometer wavelength excimer laser? And the conventional wisdom at the time was it was never going to work. There was no way you're going to get optical materials that were transparent enough at that wavelength to allow you to move ahead. There was so the lab got a consortium of the willing, sort of shown here, together to try to tackle this problem of developing the 193 nanometer lithography. So the things that had to be addressed was the photoresist, that's the sensitive layer that gets spread on the wafer itself, the optical materials that you use to make the illuminator optics and the lenses themselves, the lasers, the light bulbs, that needed work. And then ultimately you needed to put these things all together in a machine that you could use to make integrated circuits. So systematically, the lab went to work ahead at each of these issues. That image on the left is actually taken from the test and evaluation facility for optical materials that was set up in the first floor of C building at the laboratory for this period of time. And what you're looking at are 6 different samples of fused silicon material that are being irradiated with high intensity 193 nanometer illumination. And anywhere, this is an ultraviolet light, so you normally would not see it with your eyes, but anywhere you're seeing that quartz, that fused silica glow, that's a bad thing. That's material that's fluorescing and has potential defects in it. So working with a number of suppliers that I showed you on that previous slide, we're ultimately able to get to materials that would actually be useful for building projection lithography systems. On the right side is an example of some photoresist lines. These are actually pictures that were taken using one of the resists developed by our collaborators at the IBM Almaden research area, showing that you could actually pattern features down to about 1/10 of a micron with a 1/4 micron pitch. We also worked on building the first exposure tools. So shown on the left is the first all 193 nanometer stepper built here at Lincoln Laboratory. And using that stepper, we built the first transistors at 197 and used 4 different mask levels. And I actually have here, we've long since picked the bones of that stepper for other projects at Lincoln, but we did save the lens. And if you look in the middle of that photograph, this is the world's first 193 nanometer projection lens shown here. In parallel with this, we were also working with a commercial equipment supplier. That was Silicon Valley Group Lithography. They were based in Wilton, Connecticut. They were one of the US manufacturers of wafer steppers. And this is the first commercial version of a 193 nanometer stepper installed in the microelectronics lab here at Lincoln Laboratory. And that was put in place in 1994. And then using that device, we built the first 193 nanometer integrated circuits, CMOS circuits here. And for those of you from the laboratory, you recognize this is a rather iconic picture, but this is where it had its roots. So it had 13 different mass levels. So the 193 nanometer program, which finished up in sort of the 1995-96 timeframe, the results of that were significant enough that industry made the transition to 193 and used it up until that time frame that I'm showing you there. The lab didn't sit still. we said there was one more wavelength, right? There was that 157 nanometer excimer laser, further scaling the wavelength. It turns out that the optical materials there had to switch from fused silica to calcium fluoride. The quality of those materials and the abundance of those materials were not sufficient enough to support the building of commercial tools to do projection lithography. So that program terminated. We explored it. It wasn't going to be viable. So we started working on the denominator. And the laboratory did the first demonstrations of liquid immersion lithography. This is where you put a liquid between the output of that projection lens and the wafer itself, boosting the numerical aperture, allowing you to boost the numerical aperture of that projection lens. And then using that technique and multiple exposure, 193 was extended for another decade. So this is the longest serving lithography technique that's been used by the microelectronics industry to date. And then in the year 2000, the extreme ultraviolet, EUV, or soft X-ray systems came into being. So those, not using projection refractive optics, you're using reflective optics in order to make those systems work. But 193 has not ended. It's still the most largely used patterning technique used to make every modern integrated circuit today. And I show an example of the most modern tool that you can buy from ASML if you have $80 million. That, by the way, is twice the amount of money that it costs to develop 193 at Lincoln Laboratory over the decade, a single tool. And ASML sold over 100 of those last year. And using that tool, back to our human hair reference, you can print over 1 million transistors on the cross-section of a human hair. And I want to give you a size reference. This is the projection lens actual size in that 193 tool that you see up there. They wouldn't give me a real lens, and I wouldn't be able to hold it up either because it weighs 2,400 pounds, right? But this is the projection lens in a modern tool. So I will remove that later. So this is the team that made it happen, all right? And many of these folks are in the room right now. And I want to draw particular attention to the leadership team in the upper left, particularly the Lincoln leadership team, that not only fought the antibodies that were coming from both government and industry, who felt this program was a waste of time and a waste of money and would never work, but also made significant technical contributions in many of these areas. The optical materials characterization team that worked with the vendors to ultimately get fused silica material that would work at 193 and survive the many millions of exposures you'd need in a commercial system. The large photoresist development team that not only developed the materials that were sensitive to the 193 nanometer exposure, but developed the resists that had the robustness to survive the subsequent integrated circuit processing techniques. To the team that built the prototype exposure tool that I showed you, to the team that built and characterized the commercial tool, the very first commercial tool that came from SGL, and then the device design and fabrication team who actually put all those pieces together and built the first integrated circuits. So thank you. I included a slide on the citation, but you're going to see that again later. So thank you.
Well, I hope you see that to become a milestone isn't just the technology, but it's the impact that the technology made. And to make all this happen, you see that there are dedicated, not just brilliant engineers, but people who also know how to communicate that need to all the powers of be and actually get consensus to move forward with such grand initiatives. So that's something that we also celebrate today, is all the individuals and the diversity of their talents that came together to make these real and to make them practical for everyone to use and enjoy today. Our next discussion is about the semiconductor laser. And we're going to get a brief history on that. And that's going to come from Paul Juodolakis. I hope I said it right. Did I say it right? Oh, sorry. He gave me a tutorial before, but I told him when I get up there, I'll be nervous and say it wrong. So I apologize again. But Paul is the leader of the Quantum Information and Integrated Nanosystems group at MIT Lincoln Laboratory, where he leads research and development of quantum processors, quantum and classical sensors, superconducting, digital electronics, and integrated photonic technologies. Previously, Paul has led a team that developed the semiconductor slab-coupled optical waveguide amplifier, made key contributions to the development of optical sampling techniques, and has worked as a radar systems engineer beginning at the laboratory in 1988. Paul is a fellow of both the IEEE and Optica, formerly known as the Optical Society, and he holds a BS from Michigan Technology University, the MS degree from Purdue, and a PhD degree from Georgia Institute of Technology, all in electrical engineering. So Paul, please take the stage. Thank you.
Good afternoon, everyone. Thanks for joining us today. So I also am honored and humbled to be able to give this presentation. Unlike my colleagues, Craig Keast and Jim Flavin, I had no involvement in the development of the early diode laser. At the time of the early demonstrations in the fall of 1962, my parents had just met. I was -1.5. And so, however, over the past 20 years, I've had an opportunity to make contributions to diode lasers and through both technical and leadership contributions. One of the people who have been working with me for the past 20 years is Dr. Roel Swint. Dr. Swint has actually been leading a lot of the diode laser activities here at the laboratory. He also helped me put together this nomination for this milestone. Side note, Roel is also an academic grandson of one of the advisors. His PhD advisor was Nick Holonyak from General Electric, who was one of the inventors. I'd also like to point out that this is a joint milestone award between General Electric, Lincoln Laboratory, and IBM. All three of these organizations back in early '62 demonstrated this almost simultaneously and independently in that fall of '62. And so I will be presenting this more from a Lincoln Laboratory lens. If you're interested to learn more about what was happening at GE and IBM at that time, please attend their dedication ceremonies. The IBM ceremony is on the 23rd of this month at Yorktown at IBM Watson. So let's time travel back to 1962. John F. Kennedy was president. Gas was about 30 cents a gallon. The Beatles were an unknown band playing dive bars in Hamburg, Germany, and Lincoln Laboratory was 11 years old. As Dr. Evans presented in his overview of the laboratory, Lincoln's always done the combination of systems engineering, prototyping analysis, as well as advanced technology development. So on the systems engineering side, the TRADEX radar had just become operational out on the Kwajalein Atoll to support the ballistic missile defense mission. The Haystack radar was being constructed up on Millstone Hill out in Westford. And Lincoln had demonstrated the Lincoln Instrument Computer, which was the first computer that you could actually put on a desk rather than taking a full room of electronics. And so this is a picture of Marianne Wilkes, who was one of the early programmers of that computer. On the advanced technology research side, the solid state division had just been stood up a few years earlier in 1958. It had evolved out of Division 3, which was called Communications and Components. And in the solid state division, they were focused on fundamental physics, crystal growth, characterization, chemistry, and components. And one of the things that they published for many, many years was something called the Solid State Research Report. And I've taken a few elements out of here from the November '62 report. There was a science paper looking at the crystallographic planes of etched germanium. So looking at surface reactivity and how different planes etched. And then also looking at the superconducting properties of metallic alloys. Here they were looking at niobium, tin, aluminum, and measuring that critical temperature. And this is actually work that has sort of fed into the superconducting qubit work for quantum computing that's going on in my group to this day. So here is the organization list from Division 8 back in 1962. It consists of a division office and 5 groups. There were 98 people in the division at that time. For comparison, our division right now has 466 as of a couple days ago in the division. And also for comparison, my group is smaller. My group is actually larger than this whole division, but it was back then. Here are the pictures of the 7 authors on that first diode laser paper. And I'd just like to draw your attention to the places where they sat in the division. So Ben Lax was the division head. Al McWhirter was an assistant head. Bob Redeker was a group leader. Herb Zeiger was an assistant group leader. And then we had 3 staff members, Bob Keys, William Craig, and Ted Quist. Unfortunately, all these gentlemen have passed away since the recent, and some of them very recently as well too, but we're fortunate to have a few members of their family here today. But it is worth noting that this collaboration happened across the division, that happens to this day, but across our division and across the laboratory as well. So one of the material systems that they were working on in the early 1960s were semiconductor crystals. So semiconductors, for those of you who don't know, are something that has electrical conductivity somewhere between a metal and an insulator. And so they would grow these semiconductor crystals, and then they would modify them to change their properties. They would put in, as they were growing the crystal, they might put in some silicon. What silicon would do is create excess electrons in the material. So now you could have a higher conductivity because of these electrons. And then they would also do something like diffuse in an atom of zinc, and the zinc had one less electron per atom. And so now that left a gap or a hole in the electrons that also allowed conduction to occur. So the zinc region is we refer to as the P-type region, the silicon region is the N-type region. And then there's a junction between to make a PN junction. They'd also would then apply top and bottom metal contacts so that they could connect an electrical circuit around the device. And here I'm showing an electrical power source as a battery, and then a transistor, which you can think of as an electrically controlled switch. And so if we turn this switch on, the battery voltage is now applied across the device. Electrons are flowing through the circuit. They're flowing into the N-type side of the LED, and then they're flowing out this side, and when they flow out, they leave behind holes. The electrons and holes are diffusing to this junction region, and when they recombine, they give off spontaneous emission. Through the process of spontaneous emission, they give off incoherent photons. These have random phase, and they're going off in all different directions. One key metric that was important for being able to determine how well these devices work is called the efficiency, which is defined as the output optical power over the input electrical power. This is my only equation. And this metric here was to determine the most this could be is 1. If all the electrical energy went in and created photons, you get 1 out of that. And in those days, the efficiency of these types of devices was very, very low. But stay tuned. I'm going to show you some work that showed that you could really get higher efficiencies in these. In addition to characterizing these LEDs, you could also start thinking about making useful devices out of them. So you could apply an electrical waveform to the transistor. So when the voltage is high, you get current flow and it's generating photons. When it goes low, you get no signal out. So basically, then you could then take some electrical signal, analog or digital electrical signal, and be creating pulses of light that you could then transmit over a free space optical beam or into an optical fiber. So a key event that happened in the summer of 1962 at the Solid State Device Research Conference was a paper by Bob Keys and Ted Quist. Bob Keys presented the paper. In this paper, he showed the emission from these LEDs as a function of photon energy, and they measured the efficiency and found it to be somewhere between about 1/2 and 1. So very, very high efficiency. And there was an astonishment in the audience. And when Bob was done with his talk, one of the audience members stood up and said, that violates the second law of thermodynamics. And after the laughing kind of settled down, Bob Hall from GE stood up and explained why it didn't violate the second law. And so now everybody in the audience, it's just created a real buzz. And the researchers left the conference to go back to their respective labs. The Lincoln folks also went back to their lab to work on diode lasers. But in addition, they went back to do systems work in the true Lincoln fashion. They took those LEDs that they had, these very low powered LEDs that had to be cooled to cryogenic temperatures, and they put them in a reflecting telescope, and they pointed that telescope at Mount Wachusett, 55 kilometers away in Princeton, Massachusetts. And on the mountaintop, they had a 5-foot searchlight with a photomultiplier tube aperture, and they transmitted signals across this 55-kilometer link. And one of the things they transmitted was the WGBH test pattern. For those of you who don't know what a test pattern is, this is what the stations would put on the air after they went out at night. And so as a kid, I can remember waking up and the test pattern be on. And so you had to wait for cartoons to come on, the test pattern for it to go away as well too. So what this tells me is that they were doing this work at night. right? So they were transmitting these signals at night because during the day they were working to develop the diode laser. And so for about 4 months after that paper in the Solid State Research Conference, an article came out in the New York Times on November 1st that basically reported that General Electric and IBM had demonstrated the semiconductor laser. So they talked to some of the folks from General Electric, from IBM, and they also reached out to a spokesman from MIT and said that the Lincoln team is not claiming priority. GE achieved success a week or a couple of days before the MIT group. But this was, made the big splash, and they were saying that this is going to be the future of communication by light waves. So now let's think about how it was reported out in the technical literature. So going back to that research conference up in Durham, New Hampshire, after the conference, all of the researchers went back to their respective labs, and this is before the internet, right? So they had to take the paper copy from the conference and drive it back in their cars and share it with their colleagues back there. So it went back to the labs all here in the New England region. And then the first paper came out from the GE Schenectady group, Bob Hall and his team. And I want to point out 2 things here. This is the receive date, which is the date where the journal received it. So here in those days, it would have come in the mail to them. And this was the date that was published in the journal. So the second paper came out from Marshall Nathan and his team at IBM, received on 4 October 1962 and published on November 1st. These are the 2 papers that came out on November 1st. And then so it came in a couple of weeks after the GE Schenectady paper. Then the GE Syracuse paper came out, once again, submitted a couple of weeks later, published on December 1st. And then the Lincoln Laboratory paper received on November 5th and published on December 1st, the same date as the GE Syracuse paper. And so what I find interesting is that these 4 results came from these really high power research groups all up in the Northeast. And another thing too is in a retrospective that Bob Redeker published in 1987, he was talking about how he felt that he had mentioned to Ben Lax that all of our work up on top of the roof and on top of the mountain and stuff like that was delaying the development of the laser and that they might get scooped. And so in some sense, they did a little bit here, but they were still doing, in a true Lincoln fashion, they were doing systems work and device development work at the same time. So here's a slide just talking about that first diode laser. And what they did that was different from the LED is they made it longer than it was wide, and they put full metal contacts on the top and bottom. And then what they did, which was critical, is they formed an optical cavity by polishing these facets, the front facet and the back facet right here. What that allowed is the process of stimulated emission to be able to amplify the photons that were being generated. And these photons bounce back and forth, and then some fraction of them come out the polished facets. And the way that they used a number of different techniques to note that this had occurred, one of them being that they looked at the spectral narrowing that occurred. So here was below threshold. So here it's acting like a light emitting diode. And then when they got up above threshold, they actually started getting the spectral narrowing, showing that it was generating coherent photons or photons that were all in phase. So the electromagnetic field of these photons all lining up. Important to note, this is at cryogenic temperatures, so liquid nitrogen temperatures, and also the threshold, the currents were pretty high. They were pumping these things with hundreds of amps and stuff like that. So they weren't using a battery here. There was a high current pulse source coming out there. And so there's a lot on this slide, but it really just points out that Lincoln Laboratory has been doing work continuously in this area for the past 60+ years, from these early days of efficient LEDs and diode lasers, really looking at materials across the wavelength spectrum from the ultraviolet to the long wave infrared. A number of firsts came along here, 2D laser arrays, high power tapered amplifiers, and the slab coupled optical waveguide laser, and then different ways of combining these. There have been a number of spin out companies. Lasertron was spun out to commercialize the indium gallium arsenide phosphide laser that became the workhorse of the telecom revolution. And then TerraDiode was spun out to commercialize wavelength beam combining. And where I got involved personally was in early developments of the slab coupled optical waveguide amplifier, and then a variety of these applications of the amplifier since that time. And then just even really recently, last year, we had a result on indium phosphide quantum dot lasers grown on silicon, and this is a collaboration with the University of Illinois. So not to be outdone, our colleagues in our systems groups have been doing work in technology over these years. So here's some work for the free space laser comm that's been going from space, as Dr. Evans was mentioning earlier. So this is a recent result on the terabyte infrared or T-Bird satellite, which they downloaded 200 gigabit per second from 500 kilometer low Earth orbit. And this was using telecom components. And in the T-Bird satellite, there were 10 semiconductor lasers for generating the optical signals, and then also pumping optical amplifiers for boosting the signal before it was transmitted down to the ground. And so if we look in the broader world, I'd really like to say that, semiconductor lasers are really one of the founding pedestals of the information age. They're used in a variety of communication modalities, from, using as signal sources and pump diodes in undersea cables, 1.4 million kilometers of undersea cables. In data centers, every time you Google silly cat videos, it's going into a data center and using fiber optics here. And then also closer to home, in your area, every time you make a cell phone call, it goes out to a local cell tower, it gets onto an optical fiber, it goes across the country, and it comes out on another cell tower, and then it's going to your cell phone on the other end. And if you have fiber to the home, every time you're watching Netflix, it's coming over fiber optics that are using semiconductor lasers. And there's a variety of other places where they're used. Computer mice, CDs, DVDs, medical barcode scanners, medical applications, lasers for cutting and welding, and then also things like remote sensing. Here's some work we did with a company called Bridger Photonics, where they're developing a methane gas mapping sensor for working to fight climate change. And so I'd like to leave you with a quote from Time magazine in 1963. If the world is ever afflicted with a choice between thousands of different TV channels, a few diodes with their feeble beams of infrared light would carry them all at once. So this is a very prescient foreshadowing of what semiconductor lasers have enabled. And to me, it's also just really amazing what these 4 groups from 3 organizations in the Northeast of the United States did 62 years ago to really provide all this capability to us now and into the future. So with that, I have some acknowledgements as well. This is really focused on this milestone. Once again, I'd like to thank Will Swint, Joe Campbell and Jim Kuchar from the head of our Professional Societies Committee, Eric Evans and Bob Loyne from the Director's Office for motivating this work, and then folks from our library, archives, and technical communications who helped me put this talk together. And then I'd also like to give a shout out to all the compound semiconductor technologists who have been working on this technology for the past 60+ years. I'd like to recognize our partners at IBM and GE Research who helped put together this joint milestone, and also the endorsers, Jim Coleman from UT Arlington, that's actually Rule's advisor, and then Russ Dupuis from Georgia Tech. Folks from the Photonics Society, Renee Jean Essiambert, past president, and then Doug Rosano and Lauren Meekum, who are all here in the audience with us today. And then folks from the IEEE, from Schenectady section, the New York section, Boston section, and the folks from the Milestone Administration as well too. So with that, thank you very much.
It is time to present the milestone events. With that, now it is my honor to introduce our president-elect, Dr. Kathleen Kramer. Kathleen Kramer is the 2024 IEEE president-elect, which means she will be president of IEEE in 2025. And for those of you who don't know, IEEE has reached almost 500,000 members worldwide. So Kathleen has quite a task ahead of her, and she is going to carry that out flawlessly. And we are so honored to have her here today. She is a professor of electrical engineering at the University of San Diego in California. Her teaching interests are in the area of signal processing, mechatronics and robotics, and communication systems. She has previously held technical staff positions at Viasat, Hewlett Packard, and Bell Communications Research. She is a distinguished lecturer for the IEEE Aerospace and Electronic Systems Society and served on the IEEE Board of Directors as Secretary and Chair of Governance, and as the IEEE Region 6, which is the Western USA, Director. She received a BS degree in electrical engineering with a second major in physics from La Jolla Marymount University, and the PhD, MS and PhD degrees in electrical engineering from the California Institute of Technology. So please welcome our IEEE President-elect, Dr. Kathleen Kramer.
Hello, everyone. Thank you for welcoming me to today's celebration. While I've had the privilege of participating in several milestone dedications in the past, today is my first dedication as the 2024 IEEE President-elect. And it's for 3 milestones, as I pointed out to President Coughlin this morning. These ceremonies are joyful to me as we have the opportunity not only to celebrate, but to observe and preserve recognition of the pioneering technical research and developments and the women and men behind them. In this case, many men. They have shaped the trajectory of technology, our communities, and institutions. It's my pleasure to acknowledge my colleagues, Myra Marquez Samri, chair of the Boston section, fellow chair, Bala Prasanna, the director of IEEE Region 1, and Karen Panetta, who's been guiding our ceremonies this afternoon, and many others that I've met here today, and my new friend, Joe Campbell. And to share a welcome to all the members from the Boston section. I'd like to thank Eric Evans, director of Lincoln Laboratory, for his generous leadership and hosting us this afternoon as we welcome and celebrate the historical significance of this site and the innovative spirit and groundbreaking work that took place here and continues to take place here. For those who might possibly be here and somehow are unfamiliar with IEEE, we are an association dedicated to a clear and simple mission of advancing innovation and technological excellence for the benefit of humanity. One way we do this is by helping not only our members, but also the entire global community to understand how technology can be used to solve important problems and to provide solutions to such life-altering issues as sustainable design, climate change, clean water, reliable energy, connecting the unconnected, and enabling access to healthcare and education. IEEE is a world leader, a world-leading publisher of trusted, high-quality technical information, a principal organizer of international conferences, the leading advocate for education in engineering and computing, and a developer of widely used international standards. We bring together not only electrical, electronic, computing engineers, but also technologists from the fields of computer sciences and information technology, physical sciences, biological and medical science, mathematics, technical communications, education, management, law, and policy. Our worldwide membership is the heart of IEEE. In more than 190 countries, IEEE members come together forming an international professional community. This global network provides unique opportunities for our members to connect with experts shaping cutting-edge research around the globe, to develop technical standards with international reach, and to foster and grow top technical talent worldwide. IEEE's legacy is a story of innovation and collaboration. In fact, we're celebrating our 140th anniversary this year, twice as much as 70, which is quite a lot. Our founders came together in 1884 in a spirit of cooperation to support the public with technological improvements. And since then, IEEE has been fostering technical advancement for the benefit of humanity. Our professions have a long, rich, and important history, and it is essential that our pioneering technological developments and discoveries and the people behind them are recognized and celebrated for generations to come. As the largest technological association in the world, it is an important part of IEEE's mission to preserve the legacy and heritage of our professions, to recognize great achievements, and to promote the importance and impact of engineering. Since our inception, IEEE has had a standing history committee that advises the IEEE Board of Directors on matters of importance to IEEE and to our professions. Our IEEE History Center has a mission to research, preserve, and promote the history of information and electrical technologies. One of the most important tasks for this history committee and its History Center is administering and coordinating the IEEE Milestone Program. This program honors significant technical achievements in our fields of interest and the associated sciences. It is funded by donations to the IEEE Foundation. Please keep that in mind. The Milestone Program recognizes great moments throughout our world's long history of technical innovation. They are a symbol around the world of how electrical engineering and computing have helped to build the modern world. IEEE milestones help to increase the public's understanding of the contributions to society made by electrical, electronic, and computer engineers, and the strides by countless scientists and technologists to improve the way people communicate, work, travel, stay healthy, and enjoy living. By celebrating the pride and prestige of our profession's contributions to history, we demonstrate how engineers, scientists, and technologists have contributed not only to our local communities, but also to our global community, helping to build today's technologically advanced world. It is my pleasure to recognize these pioneering events and the people behind them. They serve as landmarks in the progress of technology and of civilization. At this point, I'm pleased to move into the official milestone plaque presentations. First, we have the Mode S Air Traffic Control Radar Beacon System, 1969 to 1995 milestone. I will read the plaque citation. In 1969, MIT Lincoln Laboratory began developing the Mode S Selective Secondary Surveillance Radar Beacon System to enable safe air traffic control in busy spectrum congested airspace. This technology made more efficient use of the radio spectrum than previous systems. By 1995, the Mode S techniques and transmission codes became the worldwide standard for air traffic control radars. And so I'd like to ask Eric Evans and Vincent Orlando to come up for a photograph, and perhaps Vincent would like to do the honors on the cover. We have the development of the 193 nanometer projection photolithography, 1984 to 1996 milestone. I will read the plaque citation. MIT Lincoln Laboratory pioneered the research, development, and demonstration of 193 nanometer projection lithography. This technology became the dominant high-resolution patterning technique, enabling the continuous performance scaling of integrated circuits for decades. During 1984 to 1996, Lincoln Laboratory established an international research center with industrial partners and consortia to guide microelectronic chip manufacturing with 193 nanometer lithography, which paved the way for its widespread commercial adoption. And so I'd like to ask Director Eric Evans and Dr. Mordecai Rothschild to come up for the first. The citation. In autumn of 1962, General Electric's Schenectady and Syracuse facilities, IBM Thomas J. Watson Research Center, and MIT Lincoln Laboratory each independently reported the first demonstrations of the semiconductor laser. Smaller than a grain of rice, powered using direct current injection and available at wavelengths spanning the ultraviolet to the infrared, the semiconductor laser became ubiquitous in modern communications, data storage, and precision measurement systems. I'd like to ask up here Director Eric Evans and Richard Redeker, son of inventor Robert Redeker, and Susan Zeiger, daughter of inventor Herb Zeiger, for the first photo.
On behalf of the IEEE Boston section, thank you so much. And on behalf of IEEE, please stay involved because you are helping us to make a better and brighter world. Thank you.